Today we're continuing to expand our understanding of how to model interactions involving contact by considering the case where an object, which we'll consider as our system, is touching something solid in the surroundings. In general, as long as the surface of the solid remains in contact with our system, the solid exerts a force on our system. We'll call this force F sub s, the surface contact force. Let's first discuss the direction of the surface contact force. This is a subtle issue because there are lots of possibilities here. Let's try using the same kind of atomic picture we discussed for the tension force. Here we're going to think about the atoms of the solid whose surface is in contact with our system. We can again think of a kind of ball and spring picture, something like this for the solid. Once again, the springs are relaxed when the atoms of the solid are in their equilibrium positions. However, if the solid is pressed up against our object, then we would expect the spring-like bonds would not be relaxed and forces would arise. So, for example, if the solid surface was pressed directly against the block, meaning pressed in the direction perpendicular to the surface, then we would expect the spring-like bonds to be compressed, and therefore the solid would exert a force on the block perpendicular to the surface. However, if the solid surface was pressed up at an angle against our system, then we would have compression of bonds here and here, but stretching of bonds here. So we would expect the surface contact force on the block would be at an angle. So we can see there are lots of possibilities that depend on how the solid is pressed against the system. For concreteness, let's consider our system as a block, and we're going to decompose the surface contact force into two components, one that is perpendicular to the surface of contact and one that is parallel to the surface of contact. We will give these components special names. The perpendicular component we will call the normal force. Normal is just another word meaning perpendicular. We'll call the other component, the component parallel to the surface, friction. Let's be clear. Although we have separate names for these components, they're not different forces. They are parts or components of one force, the same force, the surface contact force. With this picture in mind, we can relate the direction of the components to the way the spring-like bonds are compressed and/or stretched. So the normal force on our system will be due to the compression of the bonds below the surface, which suggests the normal component will always be away from the solid, toward the system, and of course, perpendicular to the surface between the system and the solid. The friction on our system will always be away from the side of the compressed bonds, toward the side of the stretched bonds, and of course, parallel to the surface between the system and the solid. Now, here's a big caution. We said nothing about how our system is moving, so don't fall into the trap that friction is always in a particular direction, that is, always opposite to the direction of motion. The block here could be at rest, and we could still have a friction force. The block could be moving, and in fact, the friction force could be in the direction of motion. For example, if our solid is a moving conveyor belt, and we just dropped the block onto this, then the compression and stretching of atoms in the conveyor belt would be such that the friction force on the block would be in the same direction that the block would be moving. The same direction at least until the block comes up to the same speed as the conveyor belt. Now let's turn from the direction to the magnitude of the surface contact force. Here again, the magnitude of this force is a subtle issue and can vary depending upon the situation. However, there are a couple of special circumstances where we can use a model that relates approximately the magnitude of the two parts, the normal and the friction, to each other. This can be done when the system and the surroundings are both hard materials and the surface between the system and the solid is dry. Then we can relate the magnitudes depending upon whether the system moves relative to the solid or is at rest with respect to the solid. Let's consider the moving case first. Then one model that is approximately true in a number of cases is that the magnitude of the friction is proportional to the magnitude of the normal force. Or, in other words, the magnitude of the friction force is equal to a constant called mu sub k, times the magnitude of the normal force, where mu sub k is called the coefficient of kinetic friction. This constant depends on the properties of both the object and the solid in contact with the object. In this case, the friction force is called sliding friction. Now, if the system is not moving relative to the solid in the surroundings, then generally the surface contact force adjusts, meaning the spring-like bonds in the solid in the surroundings compress and stretch in such a way as to keep the system from moving relative to the solid in the surroundings. In this case, the friction is called static friction. Generally, there's no simple relationship between the normal and the friction components, except when the object is on the verge of slipping, that is, on the verge of moving relative to the solid in the surroundings. Then, and only then, we can use another model that is approximately true in a number of cases where the magnitude of the static friction is proportional to the magnitude of the normal force. Or in other words, the magnitude of the static friction is equal to a constant, which we call mu sub s, times the magnitude of the normal force. Here, mu sub s is called the coefficient of static friction, and it's a constant that depends on the properties of both the system and the solid in contact with the system. We'll use these models in later lectures to solve problems. However, for now, we'll conclude this lecture with this question. Go ahead and give it a try. The correct answer is, we need more information. If we assume we can apply our dry friction model here, where the magnitude of the sliding friction force is proportional to the magnitude of the normal force, then, since we know the magnitude of the normal force, we could determine the magnitude of the friction if we knew the proper friction coefficient. We have the coefficient of static friction given. However, that won't help us here, as it doesn't apply here where the block is in motion relative to the floor. We need another piece of information, for example, the kinetic coefficient of friction, to find the magnitude of the friction force.